I got my undergraduate and my master's degree at the University of Rhode Island, and I did the master's at their Graduate School of Oceanography. This project in particular was a great offer, and I was really excited to, one, move into the world of modeling, and two, do something that was really applicable and actually had a direct impact on people outside of academics, the community and shellfish growers. I am working on pulling together a model that will be used to look at shellfish aquaculture potential in the Damariscotta River. This model will be able to help both presently with picking future lease sites in the next 5 to 10 years, but also looking forward 50 years or so to figure out what it might look like conditions-wise for aquaculture in the future.
We like to think of the SEANET program as sort of beginning the end of trial and error aquaculture. So if you take the perspective of an aquaculturist, they choose a site. They might take a year or two to get it permitted, and then it might be a year or two or even 3 years before they get their product onto the market. So that can be 4 to 5 years. If you make the wrong choice on site initially, you have to pay for it with 5 years of information.
I'm hoping to learn, most importantly, how climate change is going to affect these systems. So oyster and mussel growth is kind of the end product that will give us that very applicable product, but kind of subsurface to that are the changes that just the estuaries in general are going through, and how the whole system is going to respond to increased temperature, increased runoff. And so I think building this model will allow us to run all of those scenarios and get a much better idea of not only how that might affect the oysters, but you can make inferences from that to the lobster industry or the sea urchin industry. And so hopefully beyond the shellfish, it will also give us an idea of just how the coast of Maine is going to change in general. This is called a coupled modeling system, where you have the hydrodynamic model of the physics run first, and then it goes into a biological model later. And the end result is being able to run those scenarios to figure out how both the physics and the biology affects the oyster and mussel growth. This is called bathymetry, or how deep the water is, and that is actually used to generate that mesh of triangles, and the number and spacing of triangles and the size of them is just based off of how deep the water is there.
What's really innovative about our approach, I think, is to take those same tools that we've been using for water quality and start applying it to this industry, aquaculture, so that we can make viable predictions about the growth of particular species out in the environment.
Hopefully it will be able to increase the oyster and mussel aquaculture in the river, and that will provide jobs through direct farming and distribution of the shellfish, and then also provide an increase in tourism to the area. Just being out there and feeling physically the differences in temperature is a lot more meaningful than just seeing the numbers being read out on a buoy. So I love being out in the field and seeing those differences firsthand, and being able to just kind of get an idea and kind of that instinctual feeling of how the system is different from the head down to the mouth.